Chapter 14, Describing Relationships. Up to now, we've studied data that considers one variable at a time. However, most statistical studies examine data on more than one variable. The steps when trying to talk about two variables at once are the same as what we used earlier in the semester with just one variable. Always plot the data, look for the overall pattern and deviations from those patterns, and use numerical summaries. How do we graph a data set with two quantitative variables? Remember, quantitative variables are numerical variables. A scatter plot is one way to graph two quantitative variables. It shows the relationship between the two quantitative variables measured on the same individuals. Values of one variable appear on the x-axis, and if there's an explanatory variable, this is the explanatory variable. Values of the other variable appear on the y-axis, and this, if there's a response variable, this is the response variable. Now, when we're looking at a scatter plot, there's not necessarily an explanatory or a response variable. Sometimes we don't need to make a distinction. In the next chapter, we'll make a distinction. But for now, we'll just assume that if there is an explanatory, it's on the x-axis, and if there is a response, it's on the y-axis. We have an example measuring water flowing across farmland and how much soil is washed away. Erosion is a big problem for farmers. So an experiment was conducted to investigate the effect of the rate of water flow on the amount of soil washed away. The flow is measured in liters per second, and the eroded soil is measured in kilograms. So we have our data set here. We've got flow rate and eroded soil. Notice that flow rate is on the horizontal axis. That's the one that goes across. So flow rate, if we had to call one of these an x and one a y, flow rate is the x variable. Eroded soil is on the vertical axis, so a lot of you would call that the y variable. Now, how did we form this scatter plot? It has 5 dots on it, but we have 10 observations. Notice that each of these values comes in a pair. For every flow rate that was measured, we have the amount of eroded soil that corresponds to that flow rate. So we graph these as an ordered pair. Notice this first observation that we're looking at has an x of 0.31 and a y of 0.82. That's this point right here. Notice it's not quite halfway up to the number 1 on the x-axis, so 0.31 makes sense. And on the y-axis, it's 0.82. So each of these values is plotted as an ordered pair. The resulting scatter plot for the 5 ordered pairs is what you're looking at in front of you. What are we going to do with the scatter plot? Well, we're going to look for the overall pattern and for striking deviations from the pattern. We're going to look for outliers, and then we're going to describe the overall pattern by the form, direction, and strength of the relationship. For the form, we're going to use words like clustered, curved, and linear. For direction, we're going to use the terms positive or negative. And for strength, we're going to try to determine how closely the points follow a clear form. When above average values and below average values occur together, we say there is a positive association. When above average values for one variable tend to occur with below average values of the other variable, we say there's a negative association. A positive association is going to look like an uphill trend on a scatter plot, and a negative association is going to look like a downhill trend. Examples. The first scatter plot, denoting the percent of graduates taking the SAT and the state average SAT math score, has a specific trend. This is a negative association because it looks like it's going downhill as you move from left to right. So we're going to say there's a negative association here. So as the percent of graduates taking the SAT goes up, the math score goes down. So that's a negative association. And notice it looks like a downhill relationship on the scatter plot. Now, what's the form of this scatter plot? We could say a curve if we wanted. It looks like it's maybe a curved relationship. But I see two distinct clusters being formed here. So we're going to say that the form is clustered. And what about the strength of the relationship? You don't have any numbers to quantify the strength of the relationship, especially for clustered data. But we can just say it looks pretty clearly clustered. Okay, so I thought I'd take a moment to talk about this data. This is actually a phenomenon that a lot of people weren't aware of until recently when it came in the news. So when you look at this scatter plot, South Carolina is somewhere, it's one of these 2 points down here on the very bottom. I can't remember which one it is, but we usually have one of the lowest average SAT scores among the nation. We're somewhere near the bottom anyways. So a lot of people use this in political campaigns and when they're trying to raise funds for education and such. But it turns out that these states over here with a fewer percent taking the SAT have a different type of student taking it than the states that have a higher proportion taking the SAT. What's going on with these states that only have roughly 10% taking the SAT? Well, those are the students that chose to take the SAT. If only 10% of students are taking it, those are the ones that were extra motivated, probably prepared for it very well, and were better students all around. In the states where we have a higher percent taking the SAT, in this cluster, we're smashing together, we're grouping together all of the students who were motivated and prepared to take the SAT and who had really high honors classes and AP classes and were more prepared to take the SAT, and we're grouping them together with all the students who weren't that prepared to take the SAT. So what it does is it just drags the average down. It doesn't mean that our state is worse. It just means that we have a different group that's combined to make our average. So I thought that was kind of an interesting data set. Our second example is the life expectancy in years versus the gross domestic product per person in dollars. So the form of this scatter plot is pretty clearly a curve. So the form is a curve. In general, it looks like as gross domestic product per person goes up, so does the life expectancy. So we would say this is a positive association. And it's a strong curved relationship. Those points follow very closely to the curved form that we see, except for the 3 potential outliers. So when we have points that don't follow the overall pattern, and we consider them potential outliers, we like to chase down why they fall outside the overall pattern. And it turns out that these countries were ravaged by war and disease, and so it made their life expectancy go down. So that was a lurking variable. This data was taken from StatCrunch, which is a program that some of you will be using if you go on to Stat 201 at this university. And it's a repository stored in the StatCrunch software, And this is regarding EPA gas mileage reports. So we've plotted city miles per gallon against highway miles per gallon for cars. So what's the form of this one? This one looks fairly linear to me. Looks like we could fit a straight line to explain this relationship. I don't see a strong curve or a strong cluster in here. And I would say this is an uphill relationship. As city miles per gallon goes up, so do the highway miles per gallon. So this is a positive association. And I would say the relationship is moderately strong. The points are following a linear pattern, but there is a lot of spread around the line. So that's the way that we want to think about summarizing how to explain a scatter plot with those last three examples.